Welcome back. So today we're going to look at a number of PRAM algorithms which work on trees. Okay, so before we get started, many of these tree algorithms depend on a technique called the Euler-Tour technique. So we're first of all going to introduce what Euler-Tours are and then see how to construct an Euler-Tour in parallel. Okay, so given a graph, an Euler-Tour of the graph is a cycle on the graph that goes through every edge of the graph exactly once. Okay, and it can go through a vertex multiple times, but for each edge, it should go through that edge exactly once. So as an example over here, so suppose you have the graph on the right, right? And now imagine that for each of these edges, this is actually two directed edges. Okay, so for example, for this edge, imagine that we actually have two directed edges like this. Okay, and let's say that we have this for all of these edges. Okay, so in that case, an Euler-Tour of this graph would be something like this. Okay, so then you can see that as we walk around this graph, right, we are going through every directed edge exactly once. Okay, and we sometimes go through a vertex multiple times, but that's fine. Now, there's a famous theorem that says that if we're given a connected directed graph, then this graph has an Euler-Tour if and only if the in degree and out degree of every vertex is equal. Okay, and so in this case, right, remember that we're going to make an outgoing edge and an incoming edge for each node, for each edge. Okay, so therefore for each node, the in degree and the out degree are equal, right? And so by this theorem, this theorem guarantees that we do have an Euler-Tour, okay, which is what we found over here. And in fact, in general, if you have an undirected graph, right, then for any edge in that graph, you can actually make two directed edges, one in each direction. So if you do this, then you guarantee that for every vertex, the in degree and the out degree are equal. And so that graph is going to have an Euler-Tour. Okay, now since we're working with trees today, we're first of all going to see how we can compute an Euler-Tour on a tree. Okay, so for example here, in this graph, so this is a tree, and we computed this Euler-Tour. And we're going to see in general how to do this in parallel in constant time. Okay, so we can actually produce this tour in constant time. So the way we're going to do this is that every node is going to, first of all, so every node is going to look at all its neighbors, and it's just going to order the neighbors in some arbitrary order. Okay, so for example, this node 9 over here, right, maybe it orders this neighbor 1 as the first neighbor, and then second, and then third. Okay, write that a bit better. Okay, and then this 5 over here, right, it can order, maybe this node as the first one, and then this one, and then this one. Okay, so we just start with some arbitrary ordering. All right, and next, in order to compute this tour, so now the tour is actually, it's just a cycle. So it's like a linked list, right, except for the linked list wraps around on itself. Okay, so we just need a way to define this linked list. And so in other words, we need that for every node, we need to know which other node this node points to. Okay, if we know for every node which node it points to, then we've defined a linked list. Okay, and so we're going to use, we're trying to simply produce a linked list representation of the Euler-Tour. So in order to do that, what we're going to say is that suppose you have a node V. Okay. And now suppose that on your tour, you're coming into V through its ith neighbor. So remember that V is going to order all of its neighbors. Okay, so let's say that V has a total of D neighbors. And if we're coming into V through the ith neighbor, then the next edge on the tour, okay, is that we're simply going to leave V through the I plus first neighbor, through the next neighbor. Okay. However, if we're coming into V through the last neighbor, right, the D minus the dth neighbor, okay, then we're going to leave through the first neighbor. So in general, if we're coming in through the ith neighbor, we're going to leave through the I plus first modulo dth neighbor. So for example, if we, let's draw this. Okay, so if we go into 1, so 1 is also going to label all its neighbors. Okay, now 1 only has a single neighbor. Okay, so this means that if we come into 1 through the first neighbor, we're also going to leave 1 through the first neighbor. Okay, now once we leave 1 through the first neighbor, then we're coming into 9 from its first neighbor. And so by this rule that we have, right, maybe I should actually draw them in the reverse direction. So let's draw them this way. So we're going to go in over here, right? Then we're going to come into 9 through the first neighbor. And by this rule, we're going to leave 9 through the second neighbor. Okay, so we're going to go over here. Okay, and now we're coming into 3 from the third neighbor. So therefore, we're going to leave through the next neighbor, which is the first neighbor. Okay, and now we're coming into 8 through the first neighbor. And so by the rule, we're going to leave 8 through the second neighbor. Through its first neighbor. And so that means that we're going to come into 5 through the first neighbor. And so we're going to leave through the second neighbor. Okay, and now 4 here, he might have ordered these nodes in some fashion. So let's say he did this as well, let's say that this is the second neighbor, third neighbor over here. Okay, let's write this a bit nicer. 3. Okay, and then this is the first neighbor, and let's say that this is the fourth neighbor, and let's say this is the second neighbor. Okay, so in this case, since we're coming into 4 through the third neighbor, we're going to leave through the fourth neighbor. Okay, and then we're going to come back over here, right? And then we're going to go over here, we're going to go over here, right? And then we're going to go over here, here, and so on. Okay, yeah, so in this way, we're going to end up forming, we're implicitly going to create this Euler tour, because for every node, we know what the next node is on the tour. Okay, so we form this linked list, which when you put this linked list together, gives us an Euler tour. All right, and so since, in order to compute this Euler tour, all we need is that we just need to say if you're coming in through the ith neighbor, you're going out through the next neighbor, right? So that's just a constant time operation. So that means that we can actually compute this Euler tour in constant time on a tree. Okay, so now once we have this technique, we're going to use this technique plus the prefix sum technique. And we can, we'll see that we can solve many problems on trees. Okay, now remember that the prefix sum, so we actually gave a way to implement the prefix sum when your input is a linked list, right? So we did this pointer jumping technique where if you're simply given a linked list as an input, right, we can actually compute the prefix sum on that linked list. Okay. And now remember that this Euler tour that we just generated through this technique over here, right? This implicitly gives us a linked list. Okay, so then we can apply the prefix sum technique on the PRAM prefix sum technique on this linked list. Okay, so now the first problem we're going to solve is that we're going to see how to root a tree. Okay, so by that, we mean that we're going to pick an arbitrary node as the root for the tree. And then once you pick that node, then this is going to determine a bunch of parent-child relationships, right? So for example, if this is the root, right, then this node is going to be the parent of this node, right? So we want 2 to know that its parent is equal to 1. Okay, likewise, we want 3 to know that its parent is equal to 1, right? And we want 5 to know that its parent is 2, and so on. Okay, so this is what we want to do. We're given a tree, right? We can pick an arbitrary root, but once you pick that root, then this determines all of these parent-child relationships. And so we want these nodes to be able to compute for each node, we want it to be able to compute who is its parent. Okay, so to do this, what we are going to do is assign a weight of 1 to every edge in this graph. Okay, and then we're going to compute an Euler tour. So remember that in this tree, we're going to imagine that every edge, there's actually 2 directed edges, okay, 1 in each direction. And so we're actually going to assign a value of 1 on each of these directed edges. Okay, so it's going to look like this, right? Okay, and then we're going to compute a prefix sum on this Euler tour. Okay, so we have this Euler tour given implicitly as a linked list. We're going to apply our linked list prefix sum technique, and you're going to compute this prefix sum. Okay, and so let me just show you, what we get when you do that. So let's switch to a different color here. Let's say that we go for blue. Okay, so then if you do the prefix sum, this is going to become a 1, right? So this is a 2 here, 3, 4, right, and then 5, right? This is 6, 7, 8, 9, 10, 11, 12, and so on. Okay, and now we're going to use these values from the prefix sum in order to determine the parent-child relationship. Okay, so what we're going to say is that for each edge uv, okay, we're going to say that u is the parent of v whenever the prefix sum from uv is less than the prefix sum from vu. Okay, so as an example of this, so let's go for green now. Okay, so let's switch to yet a different color. So let's go for green. So for example, we have, let's say this edge. Okay, so so here we're going to say that this edge is edge 1, 2, and we're going to say that edge 1 is going to be the parent of v is going to be the parent of 2 because the prefix sum in this direction, okay, from uv, okay, is 1, whereas the prefix sum value from vu is 12. Okay, and because of this, we're going to say that 2's parent is 1. Okay, as another example, suppose that you have this node. Okay, so then here we have the nodes going from 2 to 5. Okay, and we're going to say that 2 is a parent of 5 because the prefix sum going from 2 to 5, which is equal to 3, is less than the prefix sum from 5 to 2. Okay, so so you can just check that by doing this, then every node is gonna then for every edge we can determine which direction the parent-child relationship is for that edge. Okay, so so the entire time that we need to run this algorithm for, so since we can do prefix sum in log n time, right? So this entire path has order n edges in it. So we can do prefix sum in log n time and also order n work. So therefore, we can root this tree in order log n time and order n work. Okay, so next we're going to look at the problem of so once we've rooted this tree, then that determines the depth of every node. Okay, so for example, if let's go back to red. Okay, so if this is the root over here, right, then these nodes 2, 3, 4 are at depth 1, right? The 5, 6, 7 are at depth 2, right? And then these guys are at depth 3. Okay, so now the problem we're given is that for each node, we want to compute its depth in a rooted tree. Okay, so then what we're going to do is we're first of all going to use the previous rooting algorithm in order to compute, in order to root this tree. Okay, so that every node knows its parent. Okay, so for each node v, let's let p of v be the parent of v. Okay, and next we're going to set, we're again going to put some weight on these edges. Okay, so we're going to set the weight of an edge going from the parent to the child to be 1. And then we're also going to set the weight of the edge from the child to the parent to be -1. Okay, so we're going to do this for every edge. 1, -1, 1, -1, 1, -1, 1, -1. Okay, and then again, we're going to compute a prefix sum on this Euler tour. Okay, so then when you do that, so let's do that, right? What you see is, so the value here is, this is going to be 1, right? This is going to be 2, This is going to be 1, 2. This is 1 again, right? This is going to be 2. This is going to be 3, right? Then this is going to be 2, 3, 2. What is this? 1, right? And then 0. And then 1, 0, 1, 0. Okay, so these blue values are the prefix sum. And now you can see that the depth of a node is simply the prefix sum value on the edge from the parent to the child. Okay, so for example, the depth of this node, of node 5, right, is simply the value from the parent of 5, which is 2, right, going to 5. Okay, and that value is 2 over here, right? Likewise for node, let's say 8 over here. Okay, so its depth is equal to the prefix sum value going from 7 to 8. Okay, which is 3. Okay, and the reason this works is simply because since we know what the parent-child relationship is, right? Then the way that we place these initial values, these red values, right? So every time we go down a level, okay, so the depth increases, we're going to add a 1. Okay, so that means that when you compute the prefix sum, this is going to increase the value coming into this node. Okay, and then each time you go back up, right, we are going to we put a -1, and so that means that when you compute the prefix sum, you're going to basically undo this step, this downward step that you took. Okay, so when you go down, you add a depth of 1, and when you go back up, you're going to decrease the depth by 1. Okay, so therefore, when you do the prefix sum value exactly tells you how many times you've gone down minus how many times you've gone back up. Okay, and that is equal to the depth. Okay, so then we can do this operation. So this basically involves rooting the tree and then computing this second prefix sum here, right? So both of these operations are going to take log n time, and we're going to use order n work in total. Okay, so the next problem is about computing a post-order numbering. Okay, so remember that the post-order numbering is basically for each node, we're going to visit all of its children before we visit that node. Okay, so if we so in order to do this, we need to start at a root. Okay, so let's say that let's switch back to red over here. So let's say that the root of this tree is going to be 1, right? So then the order that we're going to process these nodes is that we're going to go through for each node, we're going to process its children before we process the node itself. Okay, so therefore, if we start at 1, we're going to go down to 5, right? And then 5 is going to be the first node that we process. Okay, so then this guy should get a post order of 1, right? And then we go up to back up to 2 over here, but we're not going to process node 2. We're going to go to its children, and so then 6 is going to be the next node we process, right? And then we're going to process 8, so this guy's going to get a post order number of 3, right? And then we do 9, so he's 4, right? And then we do 7, okay? So he's 5, and so on. Okay, so then here I just listed out what the post order number is for each of these nodes. Okay, so on top we have the nodes, and on the bottom we have its post order number. Okay, so all right, and so in order to compute this post order numbering, again we're going to take this technique of setting weights on these edges. Okay. And so this time, the way we're going to set these weights is that for each node v, we're going to set the weight from v to its parent to be 1. Okay, so we're going to set, for example, these upgoing edges to be 1s. Okay, and then the down edges, right, from the parent to the node, we're going to set these to be 0s. Okay, yeah. And then you're going to compute a prefix sum, okay? And when you do this, and then we're going to compute a prefix sum on this. All right, so let's do this. Switch back to blue over here. Right, so we keep switching back and forth. So anyways, so this is going to be 0, 0. This is 1, 1. This is going to be a 2 over here. 2, 2. This is going to be a 3, 3, 4. Oops. 4, 5, 6, and then 7. This is 6, and then 7, and then 8. Okay. Yeah. So that's the entire prefix sum. And what we're going to do is we're going to set the post order numbering of each node v to be the prefix sum value from v to its parent. Okay, so for example, for this node over here, for 5, okay, so the edge from 5 to its parent, right, that's got a prefix sum value of 1. Okay, so then this guy's going to get a post order numbering of 1. Okay, and then this guy 6, right, the edge from him to his parent, right, that's going to be 2, and so he's going to get a post order of 2. Okay, and then so on. And so you can actually check that, this is going to give us the correct post order, okay, for all of these nodes. Okay, and the basic reason why this works is because, when you do this Euler tour, this in itself sort of follows the post order. Okay, the only thing you need to make sure is that, when you need to make sure that you're only going to number a node when you've visited all of its children. Okay, so coming down, right, as we come down to a node, we don't want to number that node yet, right? It's each time we go up, each time we go back up to a node through one of its children, right, we want to increase the post order of this node by 1. Okay, or actually by the number of children that we visited through this path. Okay, we want to increase the post order of this node by that number. Okay. And so by putting 1s on all of these up arrows, right, then this is what we accomplish. Okay, so again, the complexity for this is going to be order log n time and order n work. Okay, so let's do one more of these. So let's compute the number of descendants of a node. Okay, so number of descendants is of a rooted tree. So for example, if we right, so this node 1, for example, right, all of these other nodes, 2, 3, 4, all the way through 8, all of these are descendants. Okay, so then this one node, he should output a value of 8 because he's got 8 descendants. Okay, this node 2 over here, right, he's got 1, 2, 3, 4, 5 descendants, so he should output 5. Okay, so in order to do this, we're going to compute a prefix sum just like in the post order numbering. Okay, so in this post order numbering, for these downwards edges, we put a weight of 0, and then for the up edges, we put a weight of 1. Okay, and then the number of descendants of a node is equal to the prefix sum from the node to its parent minus a prefix sum from the parent to the node. Okay, so for example, if we go over here, right, so here we actually computed all these prefix sums. So if we take, so if we're trying to compute, let's say, let's switch to a green over here. Okay, so so if you want to compute the number of descendants of this node 2 over here, right, then we're going to take the value of v to its parent. Let's see, we're going to take the value of v to its parent minus the parent to v. Okay, so v to its parent, that's going to be the 6 value over here, right, and then parent to v, that's going to be 0. Okay, so then the number of descendants is going to be 6. Okay, so I guess we need to include the node itself. Okay, so wait, does that? Yeah. Right. Okay, so if we look at the number of descendants, yeah. Okay, so if we do another example, if you take this node 3 over here, okay, so then here you want to take the so it has only one descendant, which is itself. Okay, and this is equal to the prefix sum value from itself to its parent, right, minus the prefix sum from the parent to itself. Okay, so 7 minus 6, right, that gives us that this guy only has one descendant. Okay, so so this is in general how we're going to compute the number of descendants. And again, this is going to have the same log n time and order n work. All right. So we see that by applying this Euler tour technique and the prefix sum, we can actually compute many of these useful properties about the tree. Okay, so next we're going to look at another problem, and this is going to be how to evaluate an expression tree. So an expression tree is basically it's a way to represent a computation. Okay, so for example, here on the right we have this expression tree, and this is representing a computation. And what is happening over here is that so let's ignore all of these numbers in the parentheses. Okay, so we're just going to focus on the numbers in the big circles and then these operations in the big circles. So then what this is, this expression tree is saying is that we should add 4 and 5. Okay, so when you do that, then we're going to get a value of 9 over here. Okay, and then next we should multiply this 9 by 2. Okay, so you see that each of these operators, right, it's got 2 operands. Okay, so so the 2 operands are its children, and then we just perform that operation on the children, and then we get the value for the node. Okay, so then this node is going to be value 18, right? And then this over here is saying that we should add 2 and negative 5. Okay, so then this is going to become a negative 3 over here, right? This is saying that we should add 18 and negative 3, so we get a 15 over here. Okay, this is saying that we should multiply the 15 by the 2, so we're going to get a 30 over here. And this is saying that we should add the 30 and the 20, so then we're going to get a 50 over here. So therefore, this entire expression tree represents the value 50. Okay, this if you evaluate the expression tree, you're going to compute the value 50. Now, we just gave a sequential way of computing this, of evaluating this expression tree, right, by going from the leaves upwards. And so this is if you have n nodes in this tree, then this is going to take you order n time. So so now we're going to look at a way to evaluate the entire expression tree in parallel. And the main operation we're going to use is this thing called a rake operation. Okay, so a rake operation is basically, it's a way to take a tree and then make it smaller. Okay, so we're going to remove some of the nodes from the tree. And the way this is going to work is that when you rake, you have to pick a node to rake from. Okay, so in this case, for example, we're going to rake from this node 1. And what that involves is that basically we're going to take this node and its parent, and we're just going to remove them. Okay, so we're going to take these out, and we're going to take the sibling and all of its descendants. Okay, and we're going to move it to where the parent used to be. Okay, so you see that if we're going to rake 1, then we're going to get rid of, basically we're going to get rid of 1 and then get rid of 3, and then we're going to move 2 up here. Okay, so then 2 is going to point to the 4. So then after you rake, this is the situation that you have. Okay, so the way we're going to use this is that, sorry. We're going to start with the expression tree, which has many nodes in it, and then we're going to rake this tree in parallel. Okay, and each time you rake it, the tree is going to get smaller, and we're going to keep doing this until we're down to 3 nodes. And then also during this raking process, we're somehow going to keep track of the values on these nodes. Right? So remember that all of these nodes, they're going to get values if you evaluate them. Okay, so we're going to keep track of the values on these nodes as we do the raking process, and then eventually, when we've contracted everything down to 3 nodes, right, then we still kept track of all of these values, and then you can simply evaluate that 3-node expression tree, and the value you get back is going to be the same as the original value. Okay, so now first of all, let's talk about how we're going to rake this tree in parallel. Okay. So if we have many nodes, then if we want to rake these nodes in parallel, we need to make sure that we don't make concurrent changes to the same node. Okay, so for example here, right, when we were raking 1, we actually had to make some changes to what 4 was pointing to who pointed to 4, right? We had to make those changes, and so we don't want to make like concurrent changes. We don't want to have multiple nodes point to 4 at the same time in the same parallel step. So the way we're going to do this is that we're going to rake the tree starting from the bottom and work upwards. Okay, so we're going to focus on the leaves of the tree. And we're only going to look at the, so we're going to look at all of the leaves in the tree except for the first and last leaf. Okay, and we're going to call all of those other leaves, we're going to call that set A. And now we're just going to label these nodes in A, one by one. Okay, so we're going to give consecutive labels to all of these nodes in A. And by the way, all of this can be done in parallel. Okay, so we can produce all of these labels in parallel. And then once we have the labels, let's look at both the nodes with the odd labels in A and also the nodes with the even labels in A. And so what we're going to do is we're going to repeat, we're going to perform a number of rounds. In fact, log n plus 1 rounds, okay, where n is going to be the size of A. And in each of these rounds, we're first of all going to take all of the leaves in A odd, okay, all of these odd leaves, such that there are also left children. Okay, so we're not going to take all the odd leaves. We're only going to take the odd leaves who are left children. Okay, and then we're going to concurrently rake all of them. Okay, and it turns out that you can rake all of these guys who are left children. Even if you do that concurrently, we're not going to make concurrent changes to the same node. Okay, so we can actually perform all of these rakes concurrently. And then next, we're going to take the other leaves in A odd, the odd numbered leaves, but those who are right children. Okay, and then we're going to concurrently rake all of them. Okay, and then after that, what we have left are the even nodes. And then we're going to we're now going to set the set A to be these even leaves that we didn't rake yet. Okay, and then we're going to repeat the process. Okay, so we're going to take now these even leaves, we're going to renumber them, and then we're going to take the odd ones out of this renumbering, which are left children. We're going to rake them, and then we're going to rake the odd children who are the odd leaves who are right children. And then so on. Okay. So let's see an example of this process. All right. So here we're going to start with this initial tree, and then we're going to label all of the children, all of the leaves except for the first and last leaf. Okay. So therefore, we're going to give these labels to these other leaves. Okay, 1 through 7 over here. And now we're going to take all of the leaves with odd labels. Okay, so that would be the 1, the 3, the 5, and the 7. And then we first want to leave, we first want to rake these odd leaves who are left children. Okay, so that means that we're only going to rake this node 3 over here. And when you rake him, then that just means that we're going to take out the node 3, right, plus its parent, and then we're going to take the sibling of node 3, and we're going to put it where its parent used to be. Okay, so we're going to take this part over here and just move it up like that. Okay, and when you do this, you're going to get the situation in B. Okay, so next we're going to rake the other odd leaves. Okay, so so now these are going to be right children. So we're going to be raking 1, 5, and 7. Okay, and so for example, when you rake 1, okay, then we're going to take out 1 and 9, and you're just going to move 8, replace it by 8. Okay. And when you rake 5, right, you're going to take out the 5 and the 10, and you're going to move 4 up. And then when you rake 7, right, you're going to take out the 7 and 11 and move 6 up. And so after doing this, you're going to end up with the situation in C. Okay. Now, once you have this situation, then now the only leaves we have left are, these even number ones. Okay. So now we're going to renumber them from 1 to 1, 2, 3. Okay, and then we're going to take and then we're going to run another round now, and we're going to first of all take the odd numbered leaves who are left children. But in this case, we don't have any odd numbered leaves who are left children. So the next, we're going to take the odd numbered leaves who are right children. So that's going to be 1 and 3 over here, right? And these guys used to be called 2 and 6. Okay, so we're going to rake them, right? If you rake them, you get rid of this, and then you get rid of that, and then you have the situation in D over here. Okay, and then you're going to rake the right, and then you're going to redo this, and then now you're just going to rake the node 4, right? So you're going to get rid of this, and then you're going to be left with this situation over here. Okay, so that's the entire raking process. And what you can see is that as we do this, then nodes which get concurrently raked, they never have the same parent. Okay, because initially we took these odd-numbered leaves, right? But only the ones who are left children. Okay, so if you have two odd-numbered leaves who are both left children, right, then they can't have the same parent. Okay, so therefore you can rake these two guys concurrently. Okay, and each round that we do this raking process, we actually remove all of the odd-numbered leaves, right? Because if you do this, then you're going to get rid of all of these odd-numbered leaves, and you're only going to be left with the even-numbered leaves. So therefore, each raking round is going to remove half of the nodes. Okay, and so therefore, if you do this for log n+1 number of rounds, then there are only going to be 2 leaves left. Okay, so then we're going to end up with basically this situation over here. Okay, so this is how we can concurrently reduce the size of the tree. Okay. But as you do this process, as you rake this as you rake all these nodes, we need to make sure that we preserve the original value of the expression tree. And the way we're going to do that is that when you rake a node, right, we're somehow going to take the nodes that we're removing, and then we're going to incorporate their values into the nodes that we keep. Okay, so so basically we're going to combine a node that we're going to rake away with its sibling's value, because we keep its sibling. Okay, now one problem is that when you, so we're going to rake many nodes in parallel, okay? And sometimes when you do this, you could have nodes which do not have values yet, okay? So for example, suppose you have a chain graph, okay? So let's say that you have a chain graph looking like this, okay? And now you have a bunch of children, right? So let's say you have a bunch of children like this, and then you're going to rake some of these children, okay? So maybe like, you're going to rake this guy, and then this guy, and then this guy concurrently, okay? But the problem is that, as you rake these children, let's see, so some of them might not have values yet, okay? Because they're sort of like internal nodes that don't have values yet, okay? So then, so then we're going to say, so in that case, what we're going to do is we're going to assign kind of an abstract label to a node, okay? And this abstract label is going to help us keep track of the actual value of the node. So the label that we're going to assign to a node is just 2 numbers, okay? So for each node v, we're going to assign a label a of v and then b of v. And then what this a of v and b of v, this label represents is that now suppose this node v actually has a numerical value. Okay, so eventually it's going to get some sort of numerical value. Okay, even if we don't know what the value is right now, so we assume it's just some sort of number x. Okay, but then what this label represents is that the value it's a numerical label x. Okay, so if it's got a numerical label of x, then the actual value of v is going to be AV times x plus BV. Okay, right. So we're going to assign these labels to nodes, and we're going to assign these numerical label. We're going to assign these pairwise, these pairs of labels to nodes, and also numerical labels to nodes. Okay. And what these two things together mean is that the actual numerical value of a node is going to be this, AV times x plus BV expression over here. Okay, so now when you rake a node, okay, when you remove some nodes, we need to update these labels in order to preserve the values of the nodes that we took out. And so in this example over here, suppose that you're raking a node W, okay. So we're actually going to rake this node V over here. Okay, so that means that we're going to get rid of all of these nodes over here. Okay, so yeah, we're going to get rid of these nodes over here. And now suppose that for this node W, okay, we actually don't know its numerical value yet. Okay, so therefore we're just going to represent its value using some sort of x over here. Okay, so its actual value is going to be equal to AW times x plus BW. Okay, but the problem is that we don't know what x is. Okay, and then over here we have another node V that we're going to try to rake, and it's got a numerical label of CV, right? And then it's got this pair label of AVBV. So then what that means is that the actual value of this node is actually going to be equal to AV times CV plus BV. Okay. And now we have another node U over here, and let's say that its label is going to be something like AU and then BU. Okay, so now when you rake node V, what we're going to do is now this thing over here, right? So this is a multiply. So this says that we should be taking whatever value is over here and whatever value is over here, and we should multiply them, okay? And then that is going to give us the value for this node, and then the actual value for, so that's going to give us a numerical label for this node, and then the actual value for the node is going to be the label times this AU plus the BU. Okay, so in other words, now on the left here, the actual value is going to be AV times V plus BV. Okay, so it's going to be this thing over here. Okay, and then we're going to multiply that by the value on the right, which is going to be AW times X plus BW. Okay, so that's the thing on the right. So that's going to give us this numerical label over here, but then you need to multiply this by AU and then add BU. Okay. All right, so then we can take this big expression and we're going to simplify it, and we're going to pull out all of the x, all of the terms that involve x. Okay, so we're going to get this term, right? This involves x, and the rest of it is just a number over here. Okay, so x is the only thing that we don't know. Okay, so therefore we're going to have this coefficient for x. We're going to have this, this is going to be now the coefficient for x, right? And then this is going to be the other part that we add in, okay? So then now we're going to produce a new node whose numerical label is going to be x, right? And then so for the pairwise label, the A prime part is going to be this thing over here, okay? And the B prime part is going to be this thing over here. So if we do this, then then we can ensure that the actual numerical value for W is the same after raking as before raking. Okay, so that way we keep the actual values of all the nodes until eventually we're down to like 3 nodes, right? And then we can just compute the final value of the expression tree directly. Okay, so yeah, so then eventually we're going to reduce the tree down to 3 nodes, and this is going to take a log time, and then at that point we can directly get the value of the node of this entire tree. So therefore we can evaluate the tree's value in log n time, right? Because in log n time you can rake down to 3 nodes. And then each time you do the raking, right, we need to just compute these new values, but this can be computed in constant time. All right, so so let's do an example of this. So in this example, we're going to be raking some of these nodes in parallel. Okay, so the nodes that we're raking are going to be denoted by the stars. Okay, so when you when you rake this node, right? So you're going to take this out and you're going to move the -5 up. Okay. So currently the value is going to be equal to 2 plus -5, which is -3. Okay. Now when you rake the node, you're going to apply the previous operation, and you're going to convert this this 5 node, who currently has a label of 1, 0. You're going to convert that to a label of 1, 2. Okay. And what that means is that the value for this node is equal to 1 times -5 plus 2, which is -3. Okay, so we preserve the value of this node. right? So next, we're gonna keep raking, and it turns out that you can rake 2 of these nodes in parallel. Okay, so you can do this one, right? So you can get rid of this, and then you can do this one also. Okay, so when you do this, then here we're supposed to be adding the values of 4 and 5, right? Right. Okay, and so so this is going to come out to 9, right? So when you rake this, you're actually going to convert this to a you're going to change these 2 labels to this 1 and 5 here. Okay, so this indicates that this node's value is going to be 4 times 1 plus 5, which is also 9. Okay, and then and then over here we have a multiply operation. So the so we're going to change the labels. We're going to take this out, and then we're going to change the label to where did this come from? Oh, right. So we're going to move this guy up. Okay. So then the label over here, right, which used to be 1, 0, right, but it's but we're supposed to multiply by this value 2 over here. Okay. So we're just going to change this to a 2. Okay. So previously we were multiplying, whatever's on the left with this 2 here, right? So now we're just going to change the label of this to a 2. Okay, so this 2 indicates that we should multiply whatever value is, is beneath here. We should multiply that by 2. Okay, so again, we keep the same value for the overall tree. Okay, so then next we're going to rake this node. So then here we're multiplying this. Again, we're multiplying the left-hand side by this 2 over here, okay? And to do that, we're just going to change this thing to a 2 over here. Okay, so then we're going to get this situation. And then finally, we're going to rake this node over here, right? And then here we're adding 2 of these nodes. So the and then after you add them, you need to multiply this by 2, okay? So then what we're adding here, so this node, the value that's being indicated is 4 times 2 plus 10. Okay, so this is going to be 18 over here. And then this is negative 5 times 1 plus 2, so that's going to be 3 over here, right? And so what we want to do is, and then we're going to multiply this by 2. So we're going to convert, so since we're multiplying this by 2, right, we're going to convert this to a 4 and 20. Okay, so previously we were doing 2 times 4 plus 10, but if you multiply that by 2, then that means you're going to do 4 times 4 plus 20. Okay, and then you're also going to multiply this, so here you have a value of 3, and you're also going to multiply this by 2, so then you're going to get a value of 6 over here. Okay, so altogether we are doing negative 6. Right, yeah, so this is going to be negative 6. Okay, yeah, so altogether we're doing something like 4 times 4 plus 20, right, minus 6. Okay, so that's equal to 4 times 4 plus 14. Okay, so therefore when you rake this node, right, you're going to convert this label over here to this, this 4, right, and this 14. Okay, and then we're left with just 3 nodes over here, and so now we can evaluate this guy directly. Okay, so when you do this, you're going to get, so this here is going to be 4 times 4 plus 14, and then this is going to be 20 times 1, right? So which is just 20, right? And then if you add these together, you get 16 plus 14 plus 20, and so this equals 50. Okay, and this was indeed the original value of this expression tree, right? Because we saw that this whole thing is equal to 50. Okay, so that is the parallel expression tree evaluation algorithm. Okay, so we're going to look at one last algorithm, which is lowest common ancestors. Okay, so now the way this is defined is that if you have 2 nodes in a tree, okay, then so for example, I guess we're going to consider arbitrate. Yeah, so if you take this node and this node, okay, then the ancestors of the 3 are all of these nodes, right? And the the ancestors of these 6 are all of these nodes. And the LCA, or the lowest common ancestor, okay, is we're going to look at all of the nodes which are ancestors of both 3 and 6. And then you want to find the lowest one of those. Okay, so we have that 4 and 8 are both ancestors of 3 and 6. And you want to find the lowest among these 2 nodes, 4 and 8. So that's going to be node 4 over here. Okay, so it's basically, you take 2 nodes and then you draw their path up to the root. And the first place where these 2 paths meet, that's going to be the LCA. Okay, and these LCAs actually have a lot of applications. So if we can compute these things quickly, then we can use them for a bunch of other applications. Okay, so now, so today we're going to look at how to compute these things quickly in parallel. Okay, so some other examples are if you take 1 and 5, right, their LCA is going to be 4 over here. Okay, if you take 3 and 10, right, their LCA is just going to be the root node over here. It's going to be 8. Okay, so in fact, our goal for this algorithm is that if we're given a tree, then we're allowed to pre-process this tree. Okay, but after the pre-processing, then we're going to be presented with a bunch of queries for LCAs. Okay, so we're going to be given pairs of nodes, and then you want to find the LCA. And you want to find the LCA very quickly. Okay, you want to find it in constant time after you've done this pre-processing. And so, so this is the algorithm that we're going to give. Okay, we're going to show how to pre-process it, and then how to answer the LCA queries after the pre-processing in constant time. Okay, so we're first of all going to start with some simple cases. Okay, so so the simplest case is that if you have a path graph, okay, so a graph which is just like this, okay, then if you want to take the LCA of 2 nodes, right, so if you want to take the LCA of this node and that node, right, well, the LCA is just going to be whichever node is higher. Okay, so for example, this node is going to be the LCA of these 2 nodes. Okay, and so we saw some algorithms for labeling the height of a node so we can pre-process this graph so that we label all of the nodes with their heights. And then after you do that, if you want to get the LCA, you just return the lower height. Okay, and so that can be done in constant time. So that's a simple case where you can do the LCA in constant time. Another case where you can do the LCA in constant time is if you have a complete binary tree. Okay, and then suppose all of the nodes are labeled by their in-order numbering. Okay, so in order means that if you have a complete binary tree, you're going to visit the left children first, okay, and then you visit the node itself, and then you visit the right children. So that's going to produce the in-order numbering. Okay, so for example, in this complete binary tree, right, we're first of all going to visit this leftmost child, and then you're going to visit this node itself, and then you visit the right node. Okay, and then you go back up to this node, you visit it, right, and then this is going to be 5, 6, 7, and so on. Okay, so we can actually compute this in-order numbering efficiently in the pre-processing step. Right, just like we could compute the post-order numbering, you can also do the in-order numbering. And okay, so then once we have this, then in order to compute LCAs, right, so suppose you want to compute the LCA of U and V. Okay, so first of all, we're going to write their labels in binary. Okay, so let's say that U, is going to be written like this in binary, and then V is V is going to be written in the same way. Okay. And now U and V are going to differ in some bit. Okay, so let's let I be the most significant bit in which they differ. Okay, and then what we're going to do is, so then the LCA of U and V is going to be all of the bits before the ith bit. Okay, and then we're going to make the ith bit 1, and then we're going to make the other bits 0. Okay, so this is some sort of binary number. And the claim is that this is going to be the LCA of U and V. So let's do an example of this. Okay, so suppose we're trying to find the LCA of 9 and 13. Okay, so that's going to be this 12 node over here. right? So we're first of all going to write 9 and 13 in binary, right? And then we're going to look for the most significant bit in which they differ. Okay, so that's going to be this bit over here, right? And then we're going to set all of the bits before that. We're going to set all the higher order bits to 1s. Okay, so we're going to set this bit to a 1. We're going to set the ith bit itself to a 1. And then we're going to set the other bits to be 0s. Okay, and the claim is that this is going to be the LCA of 9 and 13, right? And this value is equal to 12, so that is indeed the LCA. Okay, so basically, the reason this works is that this digit I over here on which U and V differ, right? So you follow some path to go from the root. You follow some path to go from the root to U, right? And then you follow some path to go from the root to V, right? And so the first time that this path actually splits, right? That in order to get to U, you need to go, let's say, left, and then to get to V, you need to go right, right? So the first time that this path splits, that's exactly at the ith bit. Okay. And then for these lower order bits, so they're not involved in the LCA. Okay, so we just need to get the higher order bits before that path split, right? And then we need to put a 1 at the location, at the the bit number I where the path splits, and that's going to produce the LCA. Okay, so therefore all of this can be done in constant time. Okay, because we can write. We're going to assume that we can write this binary representation in constant time, and then you can find this ith bit in constant time. And so all of this just takes constant time to do. Okay, so next we're going to consider the general case where you have an arbitrary tree. Okay, and we're going to compute the LCA. We're going to see how to pre-process this tree so that we can compute the LCA in a general tree in constant time. Okay, so suppose we have suppose the tree has n nodes. Okay, so first of all, we're going to compute an Euler tour of the tree. Okay, and and then so after that you have this Euler tour, you're going to compute the we're going to label the nodes by the order of their appearance in the tour. Okay, so what that means is, so if we take this tree over here, and if you compute the Euler tour, which is given by these arrows, right, then you want to produce a list. So this is going to be this list A over here, okay? And that's going to list out all of these nodes in the order that they appear. So for example, 1 is going to appear first, right? And then we're going to go to 2, and then 3, and then we're going to go back to 2, right? And then to 4, 5, and then back to 4, and so on. Okay. So this list A here is simply writing out the this prefix sum. I'm sorry, this Euler tour. Okay. And then you can produce the list A using a prefix sum. Okay, or using pointer jumping, right? So there are different ways that we can produce this A efficiently in log time. So so we compute this this array A over here, right? And then also we're going to compute the array B, and so the B is just going to be the depth of all of these nodes. Okay, so for example, A has a depth of 0. Okay, and then 2 here, it's got a depth of 1, right? So for each time that 2 appears, we're going to just label it with 1, okay, for its depth. Okay, and we saw how we could compute all the depths of all the nodes in log time. So so we can also produce this array B in log time. Okay. Right, and the sizes of these two arrays is going to be 2n minus 1, where n is the number of nodes. Okay, so now given a level, given a node v, okay, we're going to denote the level of v to be to be the level of v. Okay, so the level of v is simply like which depth it is. Okay. And now we're also going to define this value L of v and R of v. So this L of v is going to be the index for the first occurrence of v in A. and R of V is going to be the index for the last occurrence. Okay, so for example, if you look at node 4, okay, so the first time that node 4 appears, right, the index for this, okay, so this is index 0, 1, 2, 3. So the first time it appears is at index 4. Okay? And then the last time that it appears, it's over here, right? So then this is like 5, 6, 7, 8, 9, 10. Okay, so so L of 4 is going to be the index of the first appearance, which is 4, and R of 4 is going to be the index for the final appearance, which is 10. Okay, so how can you compute these L and R values? Well, we have this lemma that says that the L of V is going to be equal to I if and only if you look in this A array at index I minus 1, okay? And the level of that node has to be 1 less than the level of V itself, okay? And then R of V is going to be equal to I if and only if you look at the next node, the next index in A, if the level of that node is going to be also 1 less than the level of V. Okay, so let's do some examples for this. So we want to say, so we know that L of 4 is equal to 4. Okay, so then what we need is that, so then by this lemma, if we look at the level of A3, okay, so A3 here is going to be this node 2 over here, right? So this node 2 should have a level which is 1 less than the level of 4 itself, okay? And indeed, the level of 2, right? So this node 2 here is at depth 1, okay? Whereas node 4 is at depth 2, okay? So the level of 2 is indeed 1 less than the level of 4. Okay, so so the reason this first part is true over here is because, you know, if it's the first appearance of 4, right? So if it's the first time that we're coming to 4, right? Then where are we coming to 4 from? We have to be coming from its parent, right? So we have to be coming to 4 through the node 2, okay? So therefore, the level or the depth of 4's parent is going to be exactly 1 less than 4's depth. Okay, so that's why we have this part over here, okay? And likewise, you have that R of 4 is going to be equal to 10, right? And so by this lemma, this says that if we look at index 11, then this guy should also have a level which is 1 less than 4's level, okay? So that means that, you know, if you look at this index 10 over here, then if you go look at index 11, the level of this, so this is going to be node 2 over here, and that guy's level is indeed 1 less than 4's level, okay? And the reason this is true is because if it's the last appearance of 4, okay, then that means that we're going back from 4 to its parent, okay? So the next node after 4 is going to be the parent, right? If it's the last appearance of 4, then the next node is going to be 4's parent. And so 4's parent is going to, the level of 4's parent is going to be 1 less than 4's level. Okay, so then using this lemma, we can actually compute all of these L and V values in parallel, in constant time, okay? Because all you need to do is, we're going to assign one processor for every value in A, okay? And that processor is just responsible for checking, so we assume that we have A and B already computed, right? And we can do that in log time, okay, during the pre-processing. And once you have this, then you can just, you can assign one processor for each value in A, and that processor can just check this condition, right? So this condition just involves reading from A and then reading from B, right? So you can get the level values from B, and then you read from A, and whenever you have this condition, then you know that you've computed either L of V or R of V. Okay, so all this can be done in parallel in constant time. Okay, so now once we have these L and R values, then now we can use them to compute the, the LCA. Okay, so we have this lemma. So the first lemma is, so this lemma says that if we have two, it's got multiple parts. So the first part is saying that if you have two nodes U and V in the tree, then if U is an ancestor of V, okay, then U is an ancestor of V if and only if you look at the L value of V, this is going to be between the L value of U and the R value of U. Okay. So, all right, so that's one part. And the second part of the lemma is saying that if you don't have this condition, okay, so for example, if R of U is less than L of V, okay, then the LCA of U and V is going to be the node with the minimum level in this interval RU to LV of A. So remember that RU is an index of A, and LV is also an index of A, okay? So if RU is less than LV, right, then we're going to look at basically a range of A, okay, from one index to a higher index. And then if you look at the levels of all of these nodes in that interval, okay, if you take the minimum level, then whichever node has that minimum level, then that is going to be the LCA of U and V. Okay, so let's first give some examples to understand this lemma. So for example, we have that node 2 here is an ancestor of node 4. And you see that the L of 2, right? So 2 first appears in index 1. Okay, so L of 2 is equal to 1. And then 4 first appears at index, 4 over here, right? So this should be 4, okay? And this 4 here is less than the final appearance of 2. Okay, so the final appearance of 2 is over here, and this is at index 11. Okay, so now this part of the lemma makes sense because, if 2 is an ancestor of 4, right, then we're first of all going to visit 2 first before we can visit 4, right? So that means that the first visit to 2 is going to come before the first visit to 4. Okay, and also the final visit to 2. Okay, so when we leave 4 for the when you leave 4, you're going to go back up to 2. Okay, so therefore the final visit to 2 is going to be it's going to come after the first visit to 4. Okay, so that's why you have the first part of this lemma over here. Okay, now as an example of the second part, we have that if you look at 2 nodes where R of U is less than L of V, okay, so for example, R of 4 is going to be equal to 10, okay, so if we're looking at nodes 4 and 8, okay, so let's erase this, so 4 and 8, okay, so their LCA is actually equal to this node 1 over here, right, and we have that R of 4 is equal to 10, and then the first occurrence of 8 is at index 13 over here, okay. So in that case, we have that the LCA of 4 and 8 is going to be the node with the minimum level in this range from 10 to 13. Okay, so the range from 10 to 13 is basically going to be this, it's basically going to be this range over here, right? And then we're looking for the node with the minimum level in this range. Okay, so that's going to be this node over here, and this is node number 1. Okay, so this is saying that the LCA of 4 and 8 is going to be node 1, which has level 0. Okay, and indeed, node 1 is the LCA of 4 and 8. Okay, so yeah, so now we can use this lemma to find LCAs in constant time. Okay, because we can first check whether this condition holds. Okay, the first part of the lemma, we can check whether that condition holds. If the condition holds, right, then the LCA of U and V is simply going to be U itself, right? If U is an ancestor of V, then U is the LCA of U and V. Okay, and otherwise, if the condition does not hold, then we're going to use this part. Okay, now the only difficulty with this part is that what this says is that we need to, so we can compute these values, RU and LV, right? So we have those values, okay? However, now what we need to do is we need to look through this, this array B within this interval over here, okay? Between R of U and L of V. And we need to find what is the minimum level in that interval. And then you need to take the corresponding node for that minimum level. So therefore, you need some way to compute the minimum level in this interval over here. Okay, if you can compute that minimum level in constant time, then we can compute the LCA in constant time. Okay, so the trick is to be able to compute this minimum level. Okay, and so now we're going to take this problem and we're going to treat it more abstractly. Okay, so we're just going to phrase this as a problem where we're given some sort of array X. Okay, so in our case, the array would be B. Okay, but in general, you could have an array X, and you're provided some interval. You're given some interval ij, and now you want to find the minimum value of X within this interval in constant time. Okay, and you're allowed to pre-process X, but after the pre-processing, then for any ij, you have to be able to find the minimum level, the minimum value in constant time. Okay, so so now this problem is going to be called the range minima problem. Okay, because we're given a range within X, and then you want to find the minima within that, the minimum value in that range. Okay, so again, the problem is that we're given an array X of size n, and then you're allowed to pre-process X, and then after doing this, then for any two indices, within the size of X, we need to be able to find the minimum value in that range in constant time. And this pre-processing is going to take log n parallel time, and it's going to do n log n work. Okay, so how do we do this? Well, for simplicity, let's assume that n is going to be a power of 2. So now what we're going to do is to form a complete binary tree with the values of X as the leaves. Okay, so if this is our X over here, right, we're going to form, so we're assuming that X is a power of 2, so we're going to form a complete binary tree on these values in X. Okay, and then, so this is going to have a bunch of internal nodes, and we're going to, so it's going to be convenient to label these internal nodes by, by these h, j values. Okay, so h is going to be the height of the internal node. So for example, these nodes over here, right, they're all at height 1, right, and then the next layer, they're at height 2, and then at height 3. Okay, and then for each layer, we're just going to label, so the second coordinate, this j thing over here, it's just, we're going to label these nodes consecutively. Okay, so this means that we're at layer 1 and the first node. Okay, layer 1, second node, and so on. All right, so then we're going to label these nodes, and now for each node, we're going to create 2 arrays. Okay, the P array and the S array. Okay, so this guy's going to have 2 arrays, this guy's going to have 2 arrays, right? So all of these nodes, each of these nodes has 2 arrays. Okay, and all of these arrays are different. Okay. Yeah, let the values of the leaf nodes. Okay, yeah. Now suppose that we're talking about one of these internal nodes. Okay. Now if you look at the subtree from that node, right? Then let's say that the values in the subtree is going to be a subrange of X. Okay. So let's say that the values in that subtree are going to start at index P in X and then go up to Q. Okay, so for example, for this guy, right, we're starting at the first value and going to the 4th value. Okay, for this guy, we're starting at the 3rd value and going to the 4th value. Okay, now what are these P and S arrays? Okay, so P stands for prefix minima. So what we're going to do is for each of these nodes, we're going to look at all of the X values in the subtree. Okay, and P is going to be the prefix minima, meaning that so P here is going to be an array. Okay, so suppose that there are going to be Q minus P nodes. Oops. Plus Q minus P plus 1 nodes. Okay, so let's call this I don't know. Let's call this what do we call this? I've used a bunch of letters, so I just want to find a letter I'm not using. So let's call this M. Let's call this M. Okay. Right. So then this P array and the S array are both going to have size m. Okay. And what this is going to be is that the kth value in this P array for this particular node hj, okay, this is going to be the minimum of the first k values in this xp up to xq. Okay. And then, yeah, so I'll give you an example of this, but let me first define this. And then for this S array, this, so here we're looking at, so when you define this P, you're starting at the first value, right? Sorry, the pth value, okay? And then you're looking towards the right, right? So you're increasing these things, okay? You're increasing the index towards the right, okay? You start at index P, and then you look at the first K values starting at index P. Now, S is going to be defined differently, okay? S, we're going to start at index Q, and then we're going to look leftwards, okay? We're going to look at the previous K values. And then you want to take the minimum value among those K values. And that's going to be S of Hj, the kth value of this array SHJ, okay? So now let's do some examples just to make this clear. Okay. So for example, let's look at the P array for node 2, 1. Okay. So for node 2, 1, we're considering this portion of X, right? Because this is the set of X which is in the subtree starting from node 2, 1. And now, in order to form the P array, what we're saying is that the first value in the P array, okay, this 5. Okay, this just comes from, we take this value over here, the 5. Okay, so the next value is going to be the minimum of these two values, of this 5 and this 10. Okay, so that's going to be a 5. Okay, so the next value is going to be the minimum of the first 3 values in this portion of X. Okay, so it's going to be the minimum of 5, 10, and 3, and so that's going to be a 3. And the final value over here is going to be the minimum of the first 4 values. Okay, so that's again going to be a 3. Okay, so that's how we define the P value for, the P array for this node 2, 1. Now, what about the S array? Okay, so for the P array, we were looking, we were starting at the first value over here, and we were looking towards the right. Okay, now for the S array, we're going to start at the final value over here, and we're going to look towards the left. And again, we're going to take mins. Okay, so therefore, for the S array, the first value is just going to be the minimum of this value, so that's just 4. Right? The next value, this 3 over here, is going to be the minimum of the first 2 values. Okay, so that's going to be a 3. Okay, the third value over here is going to be the minimum of the first 3 values, right? So that's again going to be a 3. And then the final value is going to be the minimum of all 4 values. So that's again going to be a 3. Okay. All right, so let's just do one more example to make sure this is clear. If we want to compute the P and the S arrays for this node 2, 2 over here. Okay. In this case, we're going to look at these set of values from X. Okay. So to compute the P value, so the P array, we're going to start at the 7, and we're going to look rightwards. And you keep taking the min. Okay, so the first time you take the min, it's just with the value 7, right? Next time you have the 7 and the 1, so the min is going to be the 1, right? And then you have the 7, 1, and 8, so the min is also going to be the 1, right? And then finally you have 7, 1, 8, 2, and the min is still 1. Okay, so P of 2, 2 is going to be this array. And then S of 2, 2, okay, so here we're going to go from the right to the left, right? So for the first value, that's just going to be the 2 over here, right? And then for the next value, it's going to be the min of 2 and 8, so that's again 2, right? For the third value, it's going to be the min of 2, 8, and 1, so that's going to be the 1, and then it's going to be a 1. Okay, so so this is how we define these P and S arrays. And okay, so now the claim is that suppose we can compute these P and S arrays. Okay, then we can actually compute the range minima in constant time. So we're going to do some pre-processing in order to compute these P and S arrays for all of these nodes. Okay, so here I've listed like the P and S arrays for all of the nodes, well, except for the bottom nodes. Okay, but I've listed the P and S arrays for the 3, 1, 2, 1, and 2, 2 nodes, and assuming that we have the P and S arrays for all of the nodes, the claim is that we can actually compute the range minima in constant time. Okay, and the reason is that suppose you have an interval ij, okay, and suppose you want to compute the minimum value within that range. Now, first of all, we're going to compute the LCA of I and j. Okay, but we can do that easily because remember that this tree is a complete binary tree. Okay, so we have this algorithm for computing the LCA in a complete binary tree, right? And that can be done in constant time. Okay, that was basically just to find the split point between the two nodes, right? So we have their binary representations, and then you look for the first bit where they differ. Okay, so therefore, in this for I and j, we can compute their LCA. Okay, and let's call that node V. Okay, now node V is going to have two children. Let's call these children U and W for the left and right child of V. Okay. Okay, so all right. Now x of I is going to be the pth node. Okay. X of I is going to be the pth node counting from the right in the subtree rooted at U. Okay, and then x of j. Oh, okay, right. So then we're looking for the for the minimum value within this interval from the ith value of x to the jth value of x. Okay. Now, suppose that x of I is actually so we look at this left child of V. Okay. And then if you look at the left child of V, and then you take its subtree below that left child, below U, okay? And then let's say that you start counting from the right, okay, until you get to xi, okay? And let's say that you have to count for p nodes, okay? So therefore, x of I is going to be the pth node counting from the right in the subtree rooted at U, okay? And on the other hand, for the xj, right, we're going to look for that in the W child. Okay, so that's the right child of V, right? And then for this right child, we're going to count from the left, and we're going to count for Q nodes until we get to xj. Okay, then the claim is that the minimum value in this interval from I to j is going to be the minimum between these two values. Okay, we're going to take the S array from U. Okay, and you're going to look at the pth entry of that S array. And then you're also going to take the P array from W, and you're going to look at the qth entry. Okay, and whichever one is smaller, that is going to be the range minimum between I and j. Okay, so that's probably rather confusing. So let's just do an example over here. So suppose we're trying to find the minimum value between index 2 and 5. Okay, so index 2 is going to be this value here, and then index 5, so 2, 3, 4, 5. So it's going to be this value over here, this range of values. Okay, so in particular, the minimum is actually going to be 1. Okay, now, so this is the, so the first thing we're going to do is to find the LCA of this node, right? So this is xi over here, and this is xj. Okay, so we're going to find the LCA of these two nodes, and that's going to be this node over here. Okay, and all right, and then now we're going to take the left and right children of this node. Okay, so the left child is going to be the 2, 1 node, and so this is going to be the U over here, right? And then this is going to be the W over here. Okay, and now we're going to take the so U. So U so U covers this range of values. Okay, so we're going to take the final value in the range of values in U subtree. Okay, so in other words, this 4 value. Okay, and we're going to keep counting until we get to 3. Okay, so in that case, we need to count for 2 values. Okay, so therefore this P here, this is going to be 2. Okay, so we're going to have P equals 2, okay? Because you start counting at 4 until you get to the 3. So that's 2 values, okay? And then also, we're going to look at node W, and we're going to look at the values in its subtree, which are these values. And then for W, we're going to count from the left until we get to xj. Okay, so we also are going to count for 2 values, right? And so we're also going to have that Q here is equal to 2. Okay, and now we're going to look at the S array from node U. Okay, so the S array for node U is going to be this 4, 3, 3, 3 thing over here, right? And we're going to look at the P array for node W. Okay, so the P array for node W is going to be the 7, 1, 1 here. Okay, and then we're going to look at the second entry in the so since P equals 2, we're going to look at the second entry in this S array. And since Q is also equal to 2, we're going to look at the second entry in this P array. Okay, so we have the values 1 and 3, and then you take the minimum of that, and that is actually the minimum among within this interval running from 3 to 1. Okay, so that is indeed equal to 1. Okay, so basically the reason this works is because so we have a node I over here, right, and if you have the S array, okay, so what does the S array tell you? Well, the S array tells you that if you start from this node, okay, it tells you like what is the minimum. So as you start from this node and then you go leftwards, okay, what is the minimum value? Okay, so now in our case, we found that you had to go for 2 values before you got to this 3. Okay, so that means that the minimum value within this interval over here is going to be 3. Right, so you see that the minimum value keeps decreasing as you go leftwards, right? So you have 4, 3, 3, 3. So the values can only decrease. Okay, so the smallest value basically. So what we're doing is we're splitting this entire interval from 3 to 1. We're splitting that in 2 halves. Okay, we're asking what is the minimum value in the left half, and then what is the minimum value in the right half, and then you take the minimum among those two minima. Okay, and in order to get the minimum within the left half, right, you just have to start at this final node over here, and you keep going left, and you see what is the minimum value that I can possibly encounter as I go left over here. Okay, and that's just going to be equal to this SU of 2. Okay, and then on the right side over here, you're going to the right, and then you're asking what is the minimum value I can encounter on the right, right? So that is going to be PW of 2. Okay, and the minimum of these two is going to be the minimum in this entire interval from 3 to 1. Okay, yeah, so that's why this algorithm, so that's how we do it and why this is correct. And you see that all of this can be done in constant time, right? Because given I and j, you can compute the LCA in constant time, and then you just go look in these arrays, okay? Yeah, and you can also figure out these P and Q values in constant time, right? Because you know which range of values U and W cover, so therefore you can know, where the index of P with respect to this set of values and the index of I with respect to these values and the index of J with respect to these values. Okay, so then you can get the P and the Q values, and then you just go in the array and look it up. Okay, so we're almost done here. So the final thing is that this algorithm over here assumes that you have the P and the S arrays. Okay, so the final thing is that how are we going to compute the P and the S arrays? So these we're going to compute from the bottom up. Okay, so yeah, so from the bottom up, we're going to start at the leaves, right? So the leaf is just a single value of x. Okay, so let's say x of I. Okay, so in that case, the P and the S arrays are just they're just both x. Okay, or sorry, x of I. And now we're going to go from so suppose that you've computed the P and S arrays for 2 children. Okay, for U and W, and let's say that U and W are the left and right child of node V over here. Okay, so sorry, this should be W over here. Okay. So now we're going to compute the oops, sorry. So now we're going to compute the P and VS arrays for node V. Okay. So to do this, let's let x of u be the last value in P of u. Okay. And then x of w be the last value in S of w. Okay. And then now we're going to form this new array. Okay, this is called the P prime array. Okay, so this is for this node w over here. So we have u on the left. So we have v, and then we have u, and then w. Okay, so then so we have this P of u over here, and then x of u is the last value in here. Okay, and then we have the S of w array over here, and then x of w is the last value in here. Okay. So now we're going to form a new array P prime of w. Okay. And the way we're going to do this is we're going to take, so we already have P of w. Okay. So we're going to take P of w, and we're just going to take every element of P and w and then compare that to x of u. Okay. And we're going to take the element-wise minimum of P and w, P of w and x of u. Okay. And then also we're going to compute, we're going to create this array S prime of u over here. Okay. And this is going to be the element-wise minimum of S of u, right? So we have S of u, and then we have this P of w over here. Okay. So we're going to take these two values and then take their element-wise minimum, or sorry, not this. We're going to take these two values, okay? We're going to take their element-wise minimum, okay? And this is going to produce for us this S prime of u over here, okay? And then for this P prime of w, right, we were going to take the element-wise minimum of these two values, and that's going to lead to this P prime of w over here. Okay, and then finally, we want the P of V value, P of V array and the S of V array. Okay, so the P of V array is just going to be the P of U array, right? So it's going to be this array, right? And concatenated by this array. Okay, so we're going to take the P of U and the P prime of W and concatenate them. Okay, so just P of U for the first part, and then P prime of W follows. Is the following part. Okay, so that's going to be P of U, P of V over here. And then S of V is going to be the S of W array. So it's going to be this array followed by this S prime of U array. Okay, yeah. So that's the construction. So let's give an example of this. Okay, so suppose we've already computed the P and S arrays for these two nodes, for the 2, 1 node and the 2, 2 node. Okay, and now you want to compute the P and S arrays for this node 3, 1 over here. Okay, so we're first of all going to take the final value from P of 2, 1. Okay, so that's going to be the 3, right? And we're also going to take the final value from S of W, which is going to be the 1. Okay, and now we're going to take this, right? We're going to take this value, the 3, and we're going to do the element-wise minimum of the 3 with the W. So this is going to be the U over here, and this is the W. Okay, so now we're going to take the element-wise, so this is XU over here, right? This is XU, okay, and then this is XW, okay? So we're going to take the element-wise minimum of XU with PW, okay? So that's going to give us, so the minimum of 3 and 7 is going to be 3, right? And then 3 and 1 is going to be the 1. Okay, so I'm going to, okay, oops. Okay, all right. So the element-wise minimum of 3 and 7 is going to be the 3, right? And then the for the rest of it is going to be the 1. So therefore, the P prime of W is going to be 3, 1, 1, 1. Okay, And then we're also going to take the element-wise minimum of this 1 over here with this S of U. Okay, so that's going to give us 1, 1, 1, 1. Okay, so then, so then that means that the P array for, so the P array over here is going to be this part concatenated by this part. Okay, so it's going to be 5, 5, 3, 3 concatenated by 3, 1, 1, 1. Okay, and then the S array for the S array for node 3, 1 is going to be this part, okay, concatenated by this part. Okay, so it's going to be this thing over here. Okay, right, and the basic reason why this works is because, in order to compute the P array for this 3, 1 node, right, what you want is, so this 3, 1 node covers all of these nodes, okay? Well, now the P array for this 3, 1 node for this part of the values, okay? Well, that's simply equal to P of 2, 1, okay? However, once you get into the right-hand side, right, then what is the minimum? Well, the minimum is going to be whatever. So this final value, this final value over here, the 3, okay, that is the minimum value in the entire left half over here. Okay, so therefore, if you want the minimum value in the right half, right, in both the left and the right half, you're going to have to take the minimum value from the left half, and you have to compare it against all of these elements from the right half. Okay, so for example, when you're up to the 7 part, okay, the minimum value from the 5 to the 7 is still going to be the 3. Okay. However, once you get to the 1 part, right, then the minimum value from 5 to the 1 is now going to be the minimum from the left part, which is 3, and 1. Okay, so that's going to be equal to 1. Okay, so that sort of explains why you have this P of 3, how you form the P of 3, 1. Okay, and the idea for the S of 3, 1 is the same thing. Okay, so the final thing to do is we're going to look at the time complexity for all this. So if you have a tree with n leaves, okay, then the claim is that all of these P and S arrays for this entire tree can be computed in log n parallel time and n log n parallel work, okay, total work. And the reason is that right, so we're going to go from the bottom up, right? So then given so if we're at a node, then if we know the P and the S arrays for its children, right, then we can compute the P and S arrays at that node itself in constant time. Okay, and if these two children have a total size of k, then the amount of work is going to be order k. Right, so it's constant time because, because if you look at all of these computations, right, all of these things can be computed in constant time, and then here where you form the element-wise minimum, right? Well, we assume that we have one processor per value of P of W. Okay, so therefore you can compute all of these element-wise minimum in constant time, and you can compute this S prime also in constant time. Right, and this concatenation, since you have one processor per element of U and W, you can also do this in constant time. Okay, so everything is doable in constant time, but the amount of work is simply equal to the length of these arrays. Okay, so that's going to be order k work. So that means that if you look at each layer, okay, the total amount of work for that layer is going to be order n. Okay, because for each node in that layer, the amount of work for that node is going to be order k, where k is equal to the number of nodes in its subtree, number of values of x in its subtree. Okay, so if you add together all of the nodes in a layer, right, then there are n values in the subtrees that they all cover, and so the amount of work is going to be n. Okay, order n. Okay, so each layer can be computed in order 1 time and order n work, and you have log n layers, and so therefore we get this theorem. Okay, so and it turns out that the amount of work can actually be reduced to linear, okay, if you use accelerated cascading. Okay, but basically, so what we've done is we've shown how to compute our range minima. Okay, and once you have range minima, then we can apply this to compute LCA. Okay, so if we go back, so we have to go back quite far, but oops, yeah. But anyways, if you can compute the okay, so the eraser doesn't work anymore. But if you can compute the range minima, okay, then you can apply the second part of this, and so that will allow you to compute the LCA of nodes in an arbitrary tree.